Now, let's interpret all this. So here's a picture of the dish. The dish has diameter d. It's axisymmetric. I've shown some rays here emanating from the origin, which is the same as the focal point. And what GO is telling us is that we get a disk in front of the reflector in which we have rays traveling. But outside that disk, there's zero field. In other words, GO predicts that there will be no field out here, and there will be no field out here. There will only be non-zero fields in the cylinder whose circular dimensions are determined by the extent of the reflector, and the cylinder extends to infinity along the axis of revolution of the reflector. Now, over this disk, which is a cut through the cylinder at any distance, there will be constant phase. That was by design. And I should say, we didn't take into account the fact that the feed might have non-constant phase, but that is included in the expression for the feed normalized pattern. So we haven't neglected it in this formulation, we just haven't explicitly pointed it out. So to the extent that the feed has constant phase as a function of theta sub f and phi sub f, we have constant phase. To the extent that the feed has varying phase as a function of these variables, we will have non-constant phase. I just identified in the previous slide that we will have a magnitude taper. We have one distance r sub f here, we have another distance r sub f here, a third distance r sub f here. In general, r sub f is increasing for increasing angles of theta sub f. Therefore, we expect that the field is getting weaker and weaker, that is, the incident field is getting weaker and weaker, as rays get further and further out in the cylinder. And then we note that the reflected field is polarized completely in the plane of the disk, but not in a simple way. What do we mean by that? We mean that the polarization vector is always going to lie in the plane of this disk. It's never going to have a component which sticks out of the disk, but the way it's going to be arranged in the plane of the disk is not necessarily going to be simple. By the way, I'll note here, and we will follow up in a future lecture, it suddenly becomes clear that this is a great application for aperture integration. So in previous lectures, we may have discussed the technique of identifying a field in an aperture and then predicting the properties of the radiated field by integrating over that field in the aperture. And we certainly can do that in this case, and this will be a powerful technique. This is one way we could get the main lobe, beam width, dimensions, E and H plane, half power beam width, the first few side lobes, all using techniques we already know about, because we now have a good expression or a good way to compute the fields in an aperture in front of the reflector. Perfectly legitimate thing to do, and we will do it in a future lecture. Now, just briefly, I would like to identify a few things here that have now revealed themselves. One is this issue of aperture taper. So we know we have this 1 over r sub f dependence of the magnitude of the field incident on the point of reflection due to the fact that the distance between the feed and the point of reflection is increasing with theta f. So what I'm showing here is the distance rho sub f relative to the diameter of the dish. So this is at the vertex. This corresponds to the rim, and then I'm showing various points of reflection in between. So theta sub f equals 0 would be another way to think about this. Theta sub f equals theta naught, the angle to the rim at the other end. Now, for any given f over d, I know the relationship between all these variables, so I can compute now the factor 1 over r sub f. I could simply compute this in dB, right? So at the vertex, for example, I could say that this is 0 dB. I could use the value at the vertex as being a reference. and then compute 1 over r sub f in dB relative to that value at the vertex. And we see, in fact, that because r sub f increases, of course, 1 over r sub f gets smaller, and it gets smaller at a rate which depends on the f over d ratio. So for an f over d of 1/2, it goes down to minus 2 dB at the rim. For an f over d of 1 over 3, it gets down to about minus 4 dB at the rim. And for a dish that has f over d of 1 over 4, it goes down to about minus 6 dB at the rim. So this is generally true for axisymmetric paraboloidal reflectors. We know that just from the optics of the reflector, we will have this degree of taper. Now again, whatever taper the feed pattern contributes will be in addition to this. And you might be able to devise a feed which corrects for this taper. That's sometimes of interest. This is simply the degree of taper you get from the reflector optics alone. Okay, now polarization. We've been avoiding this up to this point, so now let's tackle it head on. Here is the polarization of the reflected field. There are several ways to compute this. Here's kind of the brute force way to do it, which turns out to be a perfectly reasonable way in this case. Here's the geometry, point of reflection, the surface, the direction of incidence, the direction of reflection. We know that the direction of incidence is r sub f in this coordinate system. We know that the direction of reflection is equal to z hat for a paraboloidal reflector. Here's the expression we derived for the surface normal. We can then compute this vector E perp. It's quite simply n hat cross S super R. For example, here's S super R, here's n hat. So we can take this cross product and we get E sub perp. And then from that we can quickly compute the remaining unit vectors E sub para super R and E sub para super I. So once I've done that, I've got everything I need to compute the polarization vector, and I've just done it here in this picture. So what this picture is it's in an aperture plane perpendicular to the axis of revolution. Here is x divided by the diameter. So the rim appears at minus 0.5 and plus 0.5 in x, and then here's y over d. So the rim appears at minus 0.5 and plus 0.5, and so this turns out to be a unit circle. At each point in the aperture, I can compute the unit vector E hat super R. Right, and that's what I'm doing here. I'm just computing that using the expression we developed on the previous slide. And here I'm doing it for a dish which has f over d of 1/4. So I say here, this is the electric field polarization in an aperture plane due to a short vertically polarized electric dipole at the focus. Right, now I say vertically polarized, that means in terms of this picture here, it's polarized this way. I would get the same picture if I rotated this dipole by 90 degrees, but the whole picture would rotate by 90 degrees as well. So that's there's no loss of generality by assuming a vertically polarized dipole. And of course, it's an electrically short dipole, or you could call it a Hertzian dipole, just for the purposes of this exercise. However, having done this, we now have this picture, and what we see is in part what we expect, and part might be a little bit surprising. For example, if we look at this plane here, by the way, which is the E plane, we see that the polarization vectors are exactly as expected. Right? The reflected field has the same polarization as the incident field. If we look at the H plane, which is this plane right here, we also see the unit vectors have the same direction that we would expect. They are cleanly polarized, uniformly polarized in the vertical direction, again, as we would expect. However, for any other plane that is not either the E plane or the H plane, we see that the polarization of the reflected field is not simple. And in fact, we see all kinds of different directions are possible here. So we note that there is depolarization outside the principal planes. Here, principal planes meaning the E plane and the H plane. Now we can repeat this experiment for another f over d ratio. This is 1/4. Now let's repeat the whole thing using an f over d of 1/2. For an f over d of 1/2, we see the polarization characteristics are much better. Notice we still see perfect polarization in the E and the H planes as we did before, but now away from the E and the H planes, we see polarization is much closer to what we see in the E and the H planes. So just to compare here, here's f over d over equals 1/4, 1/2, 1/4, 1/2. So what we note is that cross pol improves with increasing f over d. Making f over d larger makes the cross pol better. Of course, the downside of increasing f over d is going to be over-illuminating the dish, as we've discussed in a previous lecture. So there's yet another dimension to the trade-off in reflector system design. You can improve cross pol by increasing f over d, but that also increases the amount of wasted power that spills past the reflector. Summary and path forward. GEO by itself is essentially useless for analyzing the pattern of reflectors. It predicts zero field in all directions except for one. And in that direction, that is a caustic in the far field. In other words, in the far field of an axisymmetric paraboloidal reflector, all the geo-reflected rays go through one pattern angle. So that's certainly a caustic. So you predict infinite field in the far field of this reflector. This is pretty unsatisfactory as a method of computing half-power beam width or side lobe characteristics, because GEO says there are none. And the reason it says there are none is because GEO doesn't know anything about the edges of the reflector. It only knows the local properties of the surface, so that field, reflected field, is either on or off. There are some fixes to this, which I will now point out. One is to not use GEO. You could use physical optic surface integration, and we will do that in a future lecture. A perfectly reasonable way to avoid this whole problem. Second way is a way I identified a few slides back, which is to use geometrical optics only to get the fields in an aperture, and then to use aperture integration to get the characteristics of the main lobe and the first few side lobes. That is a very useful technique in a whole bunch of cases, and we will certainly address that in the future. A third way is to use GEO, but to augment it with diffraction terms. That's done using techniques go by the name of GTD or UTD. That will at least allow us to get the fields for far out side lobes. So if we use GTD, for example, we can get fields out here, we can get a back lobe, and so on. However, it will not fix this problem that we can't figure out what the main lobe looks like accurately. GTD and UTD still have this problem because neither one of them works well near caustics. However, these other two techniques are horrible for this, for figuring out what's going on in the back lobe and the side lobes, far out side lobes. Now, despite the inadequacy of GEO that we've demonstrated here, we have learned a few things by doing this analysis. First, we learned that aperture taper gets worse with decreasing f over d. We learned that cross pol in any plane perpendicular to the axis of revolution degrades with decreasing f over d. And furthermore, we've now realized that this is going to be frustrating for designing reflectors, because high f over d, which appears to be what we want in terms of these two issues, also implies over-illumination or wasted power or low radiation efficiency, however you want to characterize that. So we've started to identify some of the trade-offs in reflector intended design. This concludes this lecture on GEO analysis of axisymmetric paraboloidal reflectors.